Ladies and gentlemen, my name is Nathan Isidora, and welcome to another webinar presented to you by Philips Lighting. Today's lighting for indoor applications, and is presented to you by Konstantinos, Papapmichael. But before we started, I'd like to direct your attention to the right side hand of the screen where we have the chat box and the Q&A box. If you're facing any technical issues, please state them in the chat box, and we'll try and help you as soon as possible. And if you have any questions, please state them in the chat in the Q&A box, and we'll get to the questions at the end of the presentation. If you want to stay up to date on discussions on everything that has to do with the topic and the presenter, you should join our LinkedIn community, posted in the chat box now. And without any further ado, Papapmichael.
Thank you very much, Nathan. All thanks to the Philips Lighting University for inviting me to give this webinar. Greetings to everyone out there around the world. It's a pleasure to have this opportunity to share with you my knowledge and experience in the field of lighting controls, especially adaptive lighting controls. Let's get into it. I'll give you first a mini introduction about the California Lighting Technology Center. The way Michael Seminovich gave a talk on adaptive controls earlier, about 3 months ago, I think, and he talked about the driving forces in California. He talked about occupancy controls extensively, so I will not cover those two issues that much. Michael gave a great presentation. You can go and watch it at the Philips Lighting University website. So a little bit about the center. The California Lighting Technology Center was developed with initial funding from the U.S. Department of Energy, working with the National Electrical Manufacturers Association to try and address the issue of technology transfer from the laboratory to the marketplace. And pretty soon they came up, NEMA especially, with a business plan for a public-private collaboration and the Public Interest Energy Research Program of the California Energy Commission. So the business plan, they liked it, and they decided to fund, along with partnership with NEMA, the California Lighting Technology Center, an industry-friendly center to help NEMA members sell energy efficiency technologies in California. And they're looking for home. We found Davis, who opened the arms and welcomed us. So we moved from Lawrence Berkeley Laboratory, Michael and I, and started the California Lighting Technology Center in 2004. The mission is very, very focused. The key words there are commercialization and energy efficient lighting and daylighting. And there are 3 types of activities that we do. We started with R&D. We were pretty good, trained at Lawrence Berkeley Lab for many years, 21 years. And pretty soon we realized that field testing and demonstration were extremely critical for people to know what we do and get feedback from them. And also because we knew that in the lab we could make anything work, and usually they break when we take them out in the real world, because we know under what conditions the technology will find itself and what people will do with it. And we were doing the demonstrations. We have now more than 140 demonstrations across California, small ones, 2 classrooms, 3 offices, and so on and so forth. We realized that the workforce was not knowledgeable and trained for, especially on the new digital controls and communications. So we also started a fair type of activities with outreach, education, and training. And all of this happened in partnership with many, many partners, utilities manufacturers, end users, builders. You see them there on the list. It's amazing to me, people from so many different disciplines and industries need to work together to make things happen, to transfer technology from the lab to the marketplace. Many players need to play and work together. And it's not easy, but we are getting better at it. So here is the people. These are the people who make it happen. Quite a lot of what I will present today has been done with help of the CLTC staff. It's a mixture of architects, mechanical engineers, electrical engineers, civil engineers, lighting designers, marketing people. We all get help from the business school to address business cases. And truly the challenge that we have is the harmonization of the activities I mentioned. So when new technologies hit the market, everybody's ready to accept them, from the end user to the installers and the facility managers. And I'm going to dive into the adaptive lighting, starting with the fundamental lighting design strategy, which, as most of you truly have heard before. It's provide the right light to the right place and the right time, or when and when is needed. And the way that I interpret this, right light for me means the spectral power distribution, the composition of light in terms of how much blue and cyan and yellow and green and orange and red, the recipe, if you like, of the light coming out of the light source or the luminaire, and eventually through reflections into the space, reach our eyes. The word truly refers to the candle power distribution, or the CPD, which is the directional output and intensity of the luminaires, aiming the light to where it is that we want it as lighting designers. The when is where the controls come in, which depends on environmental conditions. Apparently, we don't need the same intensity and the same composition of light continuously. We need different SPDs and different CPDs depending on what we do and what's happening in the environment. Now, I want to think of adaptive lighting as the automated implementation of this strategy. People respond to nuisances. They don't grasp opportunities. So if I'm on my desk working and the light is not enough, it's like the end of the day and the daylight goes down, I will stand up my chair, go in and turn the light on. However, if the light is on and then the daylight comes back in later into the day or the next day, I'm not going to stand up and turn off the light because the extra light does not really disturb me. So automation is pretty critical also because quite a lot of things can happen when occupants are not there, especially with the daylighting part of the lighting control, which I will just touch today. I will just focus on electric lighting controls and will close with a little bit of the second chapter on the daylight harvesting, which is the control of the daylight itself. Take a closer look at what adaptive lighting is. Smart lighting. Automatically, that word is underlined because it's the key word there. So adaptive lighting systems are ones that automatically adjust their light output based on environmental conditions to optimize space and building performance. And if we try to fill the gaps, you will see it again, the candle power distribution and the spectral power distribution in terms of the light output. You will see environmental conditions that can be many. I put there the most important that we are facing here in California and the most promising in terms of saving energy, because again, energy efficiency is critical in the middle of the center. One is the occupancy vacancy. We need to do different things when people are in the space and when people are not. Also, light availability, which I'll talk a lot today, just the light output based on available daylight, and demand response, which is pretty important in California. Without new power plants, we need to control the peak demand, sure we don't need extra power plants. And of course, optimization of performance is maximization of comfort and well-being. We should be able to see well to do what we need to do. Well-being is the effects of lighting also on circadian rhythms that go beyond vision. I'm going to tell you a little bit on that, but I'm not a lot. And of course, the energy requirements, minimization and minimization of peak electricity demand. An early example of a smart lighting or adaptive lighting, we did that back in 2005. And you can see here it's a porch light, which has two light sources. One small LED, you see it's an amber LED, 2 watts, and a compact fluorescent lamp that produces much more light and white light. There is one photosensor up at the top which keeps both light sources off during daytime, and there is an occupancy sensor in the front that during vacancy it activates the LED, or it signals the controller to activate the LED to be more accurate, and then the CFL to be on the occupancy. We are seeing, as you know, the previous one, it had something to do with the spectra. You saw that the low level during vacancy was amber. That was partly for the sweeter light that it has. It still plays the beacon effect. You can see that from a pretty long distance as you approach the house. We do it at that time for circadian rhythms. They were not so well known and so well in demand. But spectrally tunable lighting is becoming a reality. You can hear an example on this slide And it's not hard to do. We have seen several companies putting it out there. The most common implementation is you get two different types of LED sources, usually a low CCT and a high CCT, then you dim them against each other. If one is at full output and the other is at low output, you get from the minimum, in this example, 2700, which is usually what people also do in the products that are out there, all the way to 6000 degrees Kelvin. And as you dim them across each other or against each other, you can go at a full range from 0 to 100 and any of the range of CCTs. And the 100, of course, is at 50% each of the two lamps. Now, I see quite a lot of, as I said, of products coming out there. Some are more ready for the market than others. There is a lot of R&D still happening on technology, try to make it better. And on human factors, what it is we should be doing, how should we be capitalizing on this capability and this opportunity to change the light that we give, trying to understand what people want, what's good for people. And I see quite a lot of applications benefiting from that, being candidates for the first widespread implementation from office spaces. Assisted living is a pretty good one. People live a lot indoors. So good dosage of blue during the day. If they cannot go out, it's going to boost quite a lot the reduction in their melatonin, give them better sleep at night. Hospitals, hotels, and other types of applications like that. I'm not going to touch any more on the spectral power distribution. I will just focus mostly on the intensity, the candle power distribution, and from that, mostly the total flux. We take a look at the key electric lighting control strategies. The whole list there is a pretty common list. You may have seen it. And from the high-end tuning, which is especially useful during retrofits, where you retrofit one-to-one, and the new technologies offer more light that you need. So you have the high-end tuning there, and you tune the maximum to be lower than what the system can produce. Then the occupancy vacancy in the daylight harvesting, we talked about those before. Scaling is another one based on clock, on a time clock. You do different things. Demand response, which is signals, either signals from utilities for emergency or signals about electricity changes and so on and so forth. And manual control. Manual control is last, but it's one of the most important. If we miss the manual control and people find themselves in a way where they cannot override the system, they're not going to like it. This has been our experience. And you will see the colors there on the line, and they are different for a reason. High-end tuning and the manual control, everything else can be automated. And you see here occupancy vacancy with occupancy sensors, the daylight harvesting. It can be done with clocks, but as we will see, it's much better with photosensors. The scheduling directly on clocks and demand response through utility signals. The reason for the different colors is that each one of these automated approaches or strategies, they have different challenges in their implementation. Scheduling out of the way because it's really easy. It's a no-brainer. It's very, very easy once you decide what you want to do, when you want to do it. The occupancy vacancy in the daylight harvesting are pretty hard. And the challenge there is to understand what's happening in the space, if there are people or not, and if there are daylight changes or not. It's very to say I'm going to sense people, I'm going to sense light, but when you try to do it, you realize that there are so many different ways that the technologies may not work or work in the wrong way. And we will explore this in more detail about daylight. Demand response is so hard, but for different reason. We know what's happening in demand response. The utility sent a signal, or we got a signal or an electricity price change. And the challenge here is to figure out what to do. In my mind, still, I have not clarified the issue, for instance, on daylight harvesting, doing the right thing, and during the peak demand hours, which is afternoon during the summer, still, if you do and you play the game right, you should have all of your electric lights off in day-lit zones. So there isn't any more to give back, and you should have to give back from whatever else lighting is on, further from day-lit zones, and over you have to understand the issue of priorities. From where do I get light from the spaces that still have electric light on? So I'm going to focus specifically on the output, not the spectral distribution, but the total flux coming out of the lamp. And I will focus on daylight availability, as occupancy and vacancy, they have been covered nicely by Michael Seminovich. The light harvesting has been, since I started my studies back in 1980, one of the most promising energy efficiency strategies. It can save energy, both lighting energy by turning the lights, dimming them down and turning them off, and also cooling energy. The electric lighting produces heat too, and luminous efficacy of daylight, especially filtered daylight, is much, much higher than any electric light we have even today with LEDs. The other thing with the day lighting that's extremely attractive is significant peak demand reduction, because we have most of the daylight when we have the peak demand during the late afternoon or early evening times during the summer. This may change with electric cars and so on and so forth, but still for the time being, the peak demand hours and the daylight availability hours coincide. I've been traveling around the country for the last 10, 15 years, and I've been taking photographs like that. I have a pretty large collection. Of course, you see what I'm after here. Beautifully day-lit spaces. Here is an airport space. You can see excellent bilateral daylighting with clear stories on the left and floor-to-ceiling windows on the right. And of course, all of the electric lights on. And here is an energy efficiency opportunity, and there are many, many of these examples. Beautiful day-lit spaces. And you can understand here that if I turn off all of those down lights from up in the ceiling, nothing will truly change into the space with so much daylight into it. Of course, I don't have to travel the country to do that. Here are buildings on our campus. This, by the way, incandescent lamps. You can get the beautiful design with the clear stories illuminating this atrium, and all the incandescent lights are on. It's like noontime, and I could resist this one, this luminaire down at the bottom left. It's on, and it's on sunlight. You cannot even see that it is on. So these are opportunities that we really need to address, and they are like widespread types of these cases where, with plenty of daylight, we have all of the electric lights on. Barriers to widespread application. The study actually by LRC, I recall that in the early 2000s or in late 90s, and the barriers that they identified are still the ones that we have today. Is the reliability of the control systems for daylight harvesting to control electric lighting, and the other is the cost effectiveness. It's too expensive. And on the reliability, is we either overdo it, occupants complain and they don't really like it, or we underdim and then we don't the energy savings. It's pretty hard to hit exactly so that people don't complain and you save as much energy as you want. The effectiveness is also a pretty interesting one. And, looking at it, the components is low. The cost of the commissioning, which is the calibration of the photosensor to see at which level of the signal of the photosensor I should start dimming my electric lights and when should they be off. It's sort of higher because it involves a person that will have to go there, experience the place, and maybe spend from 2 hours to a day or two to make it work. As we will see, many of these systems don't really work. And we will why. Actually, the joke that I make, and I'll make it today too, is that the current daylighting control systems that we have for electric lighting controls, actually, they work if you issue them, and then you lock the door and you don't let anybody in. If people come into the space, even by walking into the space, they can affect the signal of the sensor without necessarily changes in daylight. With a white shirt under the sensor, I will change the signal. The same will happen if I move with a black shirt. So if I try to move a table under sensor who was calibrated looking at a dark carpet, and now I bring a white table under it, then of course I need to do the commissioning, recalibration. That's where again I have to bring version to do it. That cost is the highest cost today, and of course the loss of employee productivity because they get disturbed by that is even higher. You can see there the equation. This is why another study that happened with the HMG group a few years ago, about a decade ago, I think, half of the systems, daylight harvesting systems, or to be accurate, electric lighting control systems for daylight harvesting, are enabled by the people, and the ones that work, they use less than 50% of the expected savings. This makes sense. The ones that they work, they are the ones that under dim, so people don't complain, but you don't get savings. And the others that do either over dim or not in ways that people like, and then they disable them. And it's easy to disable these systems. You take a tape, you call a sensor, and you have the lights on all the time. So on and taking a closer look at electric lighting control, daylight harvesting to understand the implementation. The ultimate objective is to adjust the electric lighting, and the two options that we have is either switch it on or off, or have a dim switching. And this can happen in areas actually where they have plenty of daylight, next to windows, under skylights, and it has been much easier dimming, especially with fluorescent lamps that they don't like or didn't like. Now they kind of like it more, but they didn't like to be dimmed, especially at lower levels. And then the dimming, which is much smoother, much better in terms of acceptance. You don't have a sudden change in the luminous environment that will affect your adaptation to that higher level and go to lower. And today, I think that dimming has been winning, especially with LED light sources that they love to be dimmed. And I expect that we're going to see, especially for daylight harvesting, only dimming into the future. And the next part that we have to do is to figure out how to determine how much daylight is in the space so that we can adjust the electric lighting accordingly. And two main strategies that we have is either using the time of the day with astronomical clocks for any location we know about sunrises and sunsets, so we can assume that during the daytime there is daylight. However, this may not really be the case. Another way is photosensing, where we put sensors to sense the daylight. If we look closer at the time of day controls, advantages are pretty big. It's extremely simple, it's very reliable, and it's very inexpensive. It's like the scheduling, if you like. However, the issue is, as I said before, that the assumption that we know that there will be daylight because it's 11 o'clock in the morning will always be true. So the clocks cannot really understand what the weather conditions are. If the fenestration has changed, like I moved up from my desk, I needed privacy, I adjusted my blinds, and then electric lights don't come on because it's 11 o'clock. So they don't really work, and that's the main issue, that they don't know what's happening in the space. And of course, the solution to this issue is to add the photosensing-based controls. So the time of day controls may stay as a second, if you like, level, but I expect that photosensing is going to be the main way of doing daylight harvesting. Taking a closer look at the photosensing system, you see here a graphic with two pendant luminaires, and you can see the photosensor in between the luminaires. This is a viewing angle into the space, and the photosensor passes its signal to a logic controller. The logic controller has setting points to know what kind of signal to send to the power controllers that control the power to the lamp. So this is the complete photosensing control system. And the control happens at the logic controller. I hear people say, I say that too sometimes, the photosensor turn the lights off or dim the lights down. Actually, it's the logic controller that does it, not the photosensor. The photosensor just passes a number, a signal, if you like, to the logic controller, and then the logic controller has to make sense out of it. Now, this closer look at what's happening from the photosensor to the logic controller to the power controller. I'm not going to stay on this. I don't expect you to follow it, but I want to show you the level of complexity that comes after we pass the complexity of the strategy. There's a whole other world when you try to implement with these types of controllers. The photosensor sends a signal, the controller tries to interpret the signal, and based on preset algorithms that are there, which can of course change, it produces another signal that will go to the power controllers, where the power controllers, so they can get a signal, and then they send electricity to the lamps, and they do it again through a different type of a function that's part of the ballaster of the power supply. That's how the lights dim and down. This level of complexity in this implementation, and many things can go right or wrong right at these stages. Also, other details, again, to show you the level of complexity and questions that are still issues out there. It's the potential properties. And there are two main issues there. Interestingly enough, both relating to the spectral and the directional sensitivity sensitivity. Spectral sensitivity, for instance, we want to have all the visible sensitivity. We know that we don't want to infrared, so that we don't light sun based on foot heaters that happen to be in the view of the photosensor. But should we have photopic sensitivity to account for the light that our fovea is sensitive to? I know for sure that we need to have visible sensitivity, but I'm not sure that the photopic will help that much, mainly because the lumen, the result of the photopic sensitivity, only presents the foveal vision, and it ignores the peripheral and the perception of brightness. Another one is the directional sensitivity. Should we be more sensitive under or in front of the sensor? Should we be less sensitive under it, equally sensitive? What should be the off angles? And I will talk a little bit more about that. Giving you examples, and I will pass quickly through those of what spectral sensitivity is. You can see down here the electromagnetic spectrum within the visible and the near infrared, and you see different examples of photosensor sensitivities, again from LRC from several years ago. But you see that the tendency to hit the photopic curve, which I believe is fine. Here are results from measurements that we did on several photosensors in terms of directional sensitivity. Imagine a sensor ceiling, zero incident angle is signals that come directly from the floor up onto the ceiling, and here we move to the left and to the right. We go to oblique towards the sensor, and 90, of course, trying to hit the sensor horizontally parallel to the ceiling. And you see that most of the sensors out there, they're really sensitive to what's happening under them. You see what the theoretical cosine is, which is the blue line. You also see here a theoretical flat. It's interesting because we thought, how can we have a sensor that its signal does not change if I have a moving surface moving under it horizontally, like a person with a white shirt moving around and not really affecting the signal. And we came up, if you compute the inverse square law and the cosine law, you come up with that theoretically flat, where it's much more less sensitive under the sensor. Sensitivity increases as you go to oblique, but drops dramatically if you want to have a confined field of view, which, as we will see, can be pretty critically important. Here's another example of the little cone that's around the actual photodiode. You can see that even color of that plastic in front of the sensor can have a pretty big effect. The blue line is an actual measurement with that cone painted white, and you can see that the design of that photosensor was to cut the light at about 45 to 40 degrees, and because of the white paint, the interreflections inside the cone would give quite a lot of signal all the way, as you can see here, to 10 degrees. And if the sun was right there, imagine a window being on this side and the sun hitting that area, then that signal would be pretty amplified, and all of the design of the cone for the field of view would be lost. So quite a lot of small details can make a big difference at the end. The most critical part in a photosensor-based control is the location of the photosensor. It's very hard to figure out where to put it. And there are two main attributes on placement. One is the location in the space. Should it be at the workplace? Some people suggest that, like it can easily be covered, even more affected, because my white shirt is going to be much closer to it. Should it be at the ceiling? On a luminaire, on the facade, on the roof, then where should it be looking at? To the floor, to the window, to the wall? My general advice for the systems that are out there right now is try to find a space, a location, and a view direction where you're looking at some part of the building that will be affected by people, and the one that will have kind of an equally and balanced contribution from electric lighting and day lighting. The standard ways that we have been traditionally using for placing a photosensor are the ones that I show here in extreme cases, like a closed loop sensor, as we call it, that it is usually inside the space looking at the area that we are illuminating. And it's called closed loop because the signal of the sensor is affected by the electric lighting that it controls. When a signal of the controller adjusts the electric lighting based on the signal of the photosensor, at the same time, the signal of the photosensor is being changed. And that's why it is being called the closed loop. Right, we have what's called the open loop, like a sensor that only uses daylight, and it is not affected by electric lighting that it controls. And interesting enough, as we will see, both of those have serious limitations, if you like. And open loop alone, actually, even alone cannot truly do it. The open loop alone is pretty inadequate. You can see here some measurements that we did with two sensors under skylight, one looking down, the loop, and one looking up, the open loop. You can see lines on this plot. Here on this axis on the left, you see the signal of the open loop, the green line here, and you can see it goes from 0 all the way to 7,000 units, let's say, foot candles, but it doesn't really matter when we just want relative changes in the signal. So we have a signal that has a very wide range of change and pretty fast. Here on the right axis, we have the signal of the closed loop and also the open-closed loop ratio. And you can see the signal of the loop, it is pretty low. It goes, it's under 100 units, so significantly smaller. It is easier to map output of a daylighting system in a small range, dynamic range of the photosensor signal than it is to do it in a very, very long one. You cannot have accuracy, if you like, when you have such great variation as you can have with an open loop. The dotted line in orange is the ratio of the two. If open loop was a good indicator of what's happening indoor, that line should be a straight line, and you see that it is anything but that. So open loop is not so effective. It can work, but not truly to optimize performance and give the very best results. Also be careful, because you can close loops which are better mainly because they see what's happening in the space, so you get a direct indication of what's happening in the space. But it's very, very easy to misplace them. That's why the placement is so hard. If you put it too close to the window and the view of the window of the sensor includes parts of the outdoor where it will be much, much brighter, then your sensor signal is significantly affected by outdoor light levels, and the changes of the electric light become noise. They are not strong enough when a sensor gets so much signal from the daylight. It's another case of a misplacement where a sensor is placed right above an indirect luminaire. These examples are not fictional. I have experienced them through the demonstrations that we have done, and this is how I figured out how bad they are. And the photosensor is really saturated by the electric lighting, so now daylight becomes noise. That's why I recommended before, find space that has a balanced light output from daylight and electric light, and point the sensor to that particular space. If you only have one sensor, as we will see, there are easier ways to eliminate this issue of placement, and I will talk to this the rest of this talk. We had the opportunity in 2005 to deal with a large retailer that has big stores, the Walmart folks. They have been one of the most experienced group that I have found, with so many thousands of stores around the world, all of them illuminating with skylights. They tried the closed loop approach, a sensor looking down, and they tried an open loop approach. In the beginning, when they started in the mid-90s, most of the scientific papers were recommending a closed loop, and rightly so that you see what's happening in the space. However, pretty soon they realized the limitations of the closed loop, the disadvantages, which is for them the main one, recalibration every time that they would change the display under the sensor. Imagine a calibration happening with the display having brown tints, and then the brown tints are being sold and they're replaced with white linen, and then all the lights are off, and the good has to come back and try to recalibrate. It's not so hard, but he has to recalibrate the sensor so that it works correctly again. When they realize that they have to do that quite often as they change the display in so many stores, it became a huge expense. So they moved with months, actually, from what I recall, to open loop with the sensor looking up. And of the advantage is that it's not affected by what was happening in the space. And of course, the main disadvantage was again the same, not affected by the changes in the space. You saw from the previous slide that it is not an accurate indicator of what's happening indoors. Interestingly enough, we were able to find a solution, and the solution that we came up with is combining both sensors. We call this the dual loop daylight sensing system, and you can see that we have a sensor looking down and a sensor looking up, and both report to the controller. So when the controller hears from the closed loop sensor that there is more or less light, it doesn't do anything before it checks with the open loop to see if the open loop agrees about the change. And it works pretty nicely, and I'll give you some more information about it. I'd like to mention this, that we were able to succeed in developing automatic closed loop calibration. So when things change, the linear, etc., go down there, because of the dual loop control algorithm, we can sense that change because it is from what we expect, and we can recalibrate the sensor day on the fly. On the particular, at that time, we were doing it only at night when we knew what the signal from the electric line would be. And it works pretty nicely. So it doesn't need to be commissioned, not even in the beginning, and it doesn't need to be recommissioned ever. A combination of the two proved to be very effective in reliable sensing of daylight changes. Here, how we did it, we got the Walmart lighting system and the Walmart skylight, and we created a holder there. We also put mirrors around this space to create that a large open space equivalent. And after we tortured it, we really tortured it a lot in the laboratory. Like we would come up with changing the display, quote unquote, on the floor, moving around black cloths, white cloths, also sending students and people up on the roof to block the sun and so on and so forth. And we were failing to make it fail in the laboratory. We went and we put it out on the West Sacramento Walmart store. It was 2008. It was the beginning of the financial disaster there. And I remember going there and asking them to control the lights. And of course, they were not happy. They were waiting for the Christmas period to sell products. They couldn't afford to have problems with lighting. So you can see here on the right, the plan. They gave us the 3 rows of electric lighting, and the gray boxes here are the skylights. On this skylight, we installed the actual prototype from the laboratory. You can see it here with on the left with 2 Minolta meters, one looking up, the other looking down, and tons of electronics, along with wires that were running the algorithm from a laptop back into a closet on the back of the door. The rest of the electric lighting is controlled by an open loop, which is on this skylighting here. And in fact, the fact that they didn't give us the whole store ended up being a blessing in disguise, because it allowed us to really examine and compare the two systems side by side for identical daylight conditions. And we also installed a camera next to the sensor to see what's happening in the view of the photosensor. Here you see from level what the photosensor is looking. You can see through months, in December, January, February. In December, there are quite a lot of Christmassy things being sold. And then what plastic cabinets came in January, and then in February they went into barbecue or whatever those things are. The next to the sensor were showing us exactly the sensor. You can see it here on the 25th of December, and you see the Christmassy things. Here is the signal of the sensor based only on electric lighting at night time, and you see that it is 4.75 units. And you can see here on the 5th of January, with the white plastic sort of transparent under the sensor, the electric lighting alone at night gave a 6.97 signal. That's a 47% increase. So we verified again the problem they had, and in this case, we actually quantified it. And the automatic calibration that we had was working beautifully. Here on this plot, you see time on the x-axis, and you see the calibration set point at night time, and you can see how it changes. And here is someplace here was the 5th I showed before, 5th of January, and you see that later on into January, we have even higher types of changes in the reflectance of the material underneath. Here now, the energy savings. On this plot, we have the months down there, reported monthly. Keep in mind that Walmart operates 24/7, which means that the bottom half of this plot, it's impossible to be saved. The 3 bars for every month. One is without skylights and without dimming, like what if we let the electric lighting on continuously 24/7? And you can see that the wattage, this is per luminaire, changes only per month. December and January, 31 days, February at low, and then the only range that you have is between months with 31 and 30 days. The blue, the baseline with the open loop system, and even it is not bad. It does the job. It is a little bit on the under dimming part, and it can save energy. One of the main complaints that Walmart had is that the dimming was happening too fast, both during the early morning dimming down and during the end of the day dimming up, and people were complaining. The green is the dual loop, and you see that we moved the savings from 25 to 37. That's about 50% increase in energy savings. And the most important thing that the Walmart folks appreciated is they got no complaints for the dimming of the lights. It would take much longer for the dual loop to dim lights, 2 to 3 times longer than what the open loop. Laboratory prototype, we installed it back in 2008, and here is a picture of a commercial product. Actually, you can see how large and ugly in some ways, beautiful for me still, the laboratory prototype is, and how elegant and small vessel prototype is, with 2 sensors looking up and looking down. And right now we are verifying its performance again on the same way Sacramento works. The question is, can this approach work also for side lighting? Because sky lighting, it's easy. The daylight comes in a very uniform way from evenly distributed openings on the roof from the same direction as electric lighting. So it's really the easy daylight harvesting or electric lighting control for daylight harvesting problem. Can it be for windows? And right, there was a student that did her master's actually on this project, and she did a fantastic job. And actually now she's employed by Philips in Chicago on the research group. And way to have a closed loop, you see that we had to split the 2 sensors. They couldn't be together. Closed loop can be moved around the space, and you just focus on the area that you want to control. And the rest of the sensor need to look at the window so that it is affected mostly by the daylight and be as much not affected by electric light as possible. And the good news is that it works, but it works through very expensive commissioning. And the expensive commissioning is mainly the knowledge and the time that is required to place the open loop sensor in terms of its position and the field of view. The field of view should cover only the window. The sensor should be far enough from the window. So if you have a shading system like Venetian blinds, imagine that if I bring the sensor very close to the Venetian blinds, I may risk being affected by a single blind. So I have to move it further away to get a good sampling of this area so that the blinds and the openings in between are evenly distributed within the view of the sensor. With that, because of this very expensive commissioning, this approach would not make it in the market. You cannot really find people, educate so many people and train them at that level, and also the reliability of spaces could create all kinds of different problems. So the next idea that we had, which I believe is the future, is based on the assumption that, yes, you can fool one sensor at a time, as I said, just by walking under it with black or white clothing, but fooling multiple sensors at the same time in the same way truly requires a special choreography. You can hear a schematic of what is a day lighting harvesting laboratory at the California Lighting Technology Center, with a pretty large office space where we can split it in half and have 2 individual spaces or 1 open. And you see 4 luminaires with communication capabilities, and as you will see, each one carries its own sensors. Here we have an internal facade, and in this area, especially on this wall at the bottom, we have installed what we call sky wall. And here, the internal facade, and the sky wall is a pretty large array of fluorescent lighting that was available at the time. If we were to do today, we would use LEDs, but it works pretty well. Don't try to simulate daylight. What we simulate is daylight changes. So we can easily simulate, all of these are individually dimmable by a computer. So we simulate sunrises and sunsets and partly cloudy days where the sun pops behind the clouds, etc., or different facades, or different external obstructions, like half of the facade being blocked by a tree or by another building and the other one contributing more. Here on the whole facade, we easily cut windows by holding different panes of wood or cardboard, if you like, and create different types of fenestrations to make sure that we develop algorithms for what we call smart luminaires. Smart luminaires have one or more light sources, multiple integrated sensors for occupancy, for light, for temperature, and others. You can put humidity or you can put airflow or CO2. They have communications, and they communicate both with other luminaires, with utilities, as you will see on my last slide, also possibly with Windows. And the control logic is based not only on their own sensors, but it is also based on the sensors of the neighboring luminaires. So smart luminaires have their own brains, they have their own sensors, and they can automate their operation on their own, trying to best understand what's happening, not only based on their experience with the sensors, but also because they have access to the experience of their lumens in the space. So you imagine I'm passing with a white shirt under one of the smart luminaires. That smart luminaire will see more light, but before it dims itself down, it will see that the rest of her sisters in the space didn't see that, so it will understand that something is happening under the space. So this is the new approach, and I believe that it is going to be the future for many reasons, that especially economics and reliability of you can see here how we are doing the research and development, trying to develop the algorithms. There are 4 luminaires that we're working on. You see a close-up of one right here, and you can see that we have opened here with sensors. We have 8 sensors looking down and looking in all different directions. This is for us to understand which sensors are the most useful. Expectation is that we're going to need at least 2 sensors looking at different directions. So if a luminaire is an orphan in a space, it can still have 2 different types of spilling into the room for daylight. And if they are all together, if maybe one will be enough. We'll know more by summer when we're going to see how well the algorithms that we are developing are working. I'm going to close with telling you the other half of the story of daylight harvesting, so that I was careful on saying electric lighting controls for daylight harvesting rather than daylighting controls. Because truly, when we say daylighting controls, we use it as a proxy for electric lighting controls. And this is not accurate, and we should try to consciously avoid it. I'm still trying. So I told you before half of the story. Half of the story of daylight harvesting is to reduce electric lighting based on available daylight. The rest of the story goes like this. And after the electric lighting is off, or at the minimum output, if we don't want to turn it off, there are reasons for that. Like people can get confused on why the lights turned off, so we can keep it at a minimum. But after we reach that minimum, then we start controlling the transmittance of the fenestration of the windows and the skylights, and we do that based on the HVAC status. Like, should we be heating? Should we be cooling? We are smart enough to turn lights off when there is nobody in the room. Can be smarter, and after there is nobody in the room, or we can see what to do with the windows. Like if we are in a cooling mode, just block completely the solar heat gain with a high solar heat gain reflector, or if it is the cooling season, and if it is the heating season, the HVAC is in heating mode, then we can blast the sunlight if available for that orientation without worrying about glare, because there is nobody there helping the heating system. And of course, while trying to, if people are there and we're trying to help the heating system, we should make sure that we don't overdo it, helping the heating system, and then we produce glare for the occupants. So the ultimate, and this is my last slide, is to eventually integrate electric lighting, windows, skylights, and the HVAC. And integrated control strategy that we use is very, very simple, and that's why we're hopeful that it's going to work. During occupancy, we focus on comfort, and during vacancy, we focus on energy efficiency. So comfort means adjusted fenestration for daylight penetration. That's a very first electric lighting based on the available daylight, and finally have the HVAC take care of the loads that are left. During vacancy, adjust the fenestration, but now focusing on cooling or heating. Am I heating or am I cooling? What do I need to do to help the HVAC as a window or as a skylight? And of course, the electric lighting should be turned off or down. There is nobody in the building. And of course, again, the HVAC has the easiest role there in terms of responding. It will just take care of the thermal comfort and the indoor air quality through ventilation and the heating and cooling aspects of it. And I will end. Thank you very much for your attention.
Thank you very much, Konstantinos, for that wonderful presentation. I hope everybody was paying attention. There's a lot to take away, and a very informative one at that. Thank you, Costa. Ladies and gentlemen, this is the time to ask questions. Unfortunately, due to it being such a long but also very entertaining presentation, we only have time for one or two questions. If you have additional questions and you want your questions answered, please join the LinkedIn community. You post your questions, and we'll have Costa answer as many as he possibly can. I want to read some of the questions.
I'm moving the Q&A up on the list here so that I can activate it and see. Okay, now I can see it. Questions that came early on. If it started or not, no one is speaking. Let me scroll through here. We'll start. Hi, it started. Hi, done. Yeah. Oh, I got into the questions. Let's take them in the exam. First one says, has anyone considered utilizing a voice-activated device such as Amazon's Echo Siri to allow the occupant to override or modify the system sensor? I'm pretty sure that these types of experiments are out there, but I really consider that as a no-brainer because for me, it's the equivalent of the manual control. I don't have to sense anything. Rather than having a switch, I use my mouth and then the technical problems are there, but I expect that these things will come for overriding it without having to move around. And they may be also pretty useful because in many cases, the occupants are different. I need today 3 times more light than what I needed when I was 25. So I bet you that I would like a little bit more light if I'm reading and writing, not necessarily being on the computer. So I think that those technologies will come. I don't know of any specific one though. With regard to the Sacramento Goldman study, what was the target and gain set points for the daylight sensor? Assuming the set points were consistent between the 3 levels. The question is about the set points and the way that our algorithms work are really deviating away from the traditional approaches. We don't try to correlate the signature and the work plane illuminance. In work plane illuminance, I have some slides and I removed them for the interest of time. But the work plane illuminance really is a very, very ineffective metric in measuring anything that has to do with comfort. The only reason that we use them is because it's very easy to measure and it's inexpensive. But it doesn't truly tell you much. In fact, quite a lot of the new ground that we cut with algorithms, if we threw when we threw the work plane illuminance out of the equation, and then we just assume that the electric lighting provided by the electric lighting system is enough to do the job. So algorithms are based on the signal of the photosensor based on the electric light output alone. And you have to do it at night. Just turning your lights on and off or getting them through their dimming range can give you the setting point that you want. And you saw from my presentation, this setting point continuously changes based on what's happening in the space. And in today's implementations, we change it even when somebody passes underneath with a white shirt. The changes maybe into the milliseconds part of the equation, but we don't care. That's the beauty of microprocessors. They keep on doing exactly what they are supposed to continuously. Are all LEDs dimmable? Not all of them, but the way I see it, especially for commercial applications, that's where we're going. And when we will resolve the issue, my expectation is that the LEDs, the power supply of LEDs, the controller for and the communications are all going to be on one chip. And my expectation is that with integrated circuits to adjust the power, we should be able to dim all LEDs in a beautiful way. But today, for sure, you can get especially a lamp replacement, etc., that are not dimmable. What is your view on outdoor applications? Michael covered outdoor applications quite a lot. I recommend you go to that to that presentation.
Sorry to cut you off.
I think that's it. Time. We have a minute for closing remarks from Nathan. Thank you all very much for your attention.
Again, Costa, for such a wonderful presentation and taking time to answer some of these questions. Ladies and gentlemen, if Costa hasn't gotten to your question, or if a question pops up later while you're in the bathroom or just waiting for coffee, please feel free to join our LinkedIn community and post your questions there, and we'll try and answer all of them and have a lively debate and discussion. This is Nathan Isidora for Lighting Academy, signing off. Have a great day.